Like, come forward. Come forward. Thank you.
All right, can everyone hear us? Okay. Awesome. Welcome everyone to the next Papers We Love, the current Papers We Love, the September Papers We Love. So our guest today is Yifan Xing. You're a student at Northeastern.
I am.
She's going to talk to us about an obviously popular topic because of the great turnout that we have today. So thanks everyone for coming to listen about consensus algorithms. I'm going to do some administrivia first. The usual for anyone who's been here before, if you would like to speak, let me know. We are a very friendly group. We want to hear about any academic papers that you find interesting, inspirational, or foundational. You do not have to be an accomplished speaker. First-time speakers are more than welcome as well. And yeah, we're always looking for interesting topics to listen about. We're actually going to be sending out a Google form relatively soon, both to the meetup, and then we'll also announce it on the Twitter feed, which is how we will sort of more directly try to canvas for next round of talks from everyone. So look forward to that. And other than that, please welcome Yifan, and let's get started.
One question.
Yeah.
I see that the mic it's muted. Is that something?
That's the computer that's muted. Yep.
Okay, great.
That's so that it's not going to do
Just
feedback.
checking.
Yeah, no problem. Thank you for asking.
Yeah, of course. So hi everyone. Welcome to the How to Pick a Cake Flavor talk. I'm just kidding. Well, we're going to talk about that later. That's definitely one of the things on the agenda. Let me just start my timer. Okay, great. Welcome to the talk about consensus algorithms. I'd like to do a poll first to start the talk. So if you'd indulge me and if you can pull up your phone and go on this website called Slido. Let me just display on the... So if you can go search Slido and then enter this code, you will be able to see this question. And please answer. Let me know if anyone have any problem getting to the poll. Oh, there we go. Someone responded. Okay, more. So when we talk about distributed system related softwares, it could be anything like email, web browsers, because they all underneath use distributed system like algorithms. And ooh, I see no started decreasing. That's good. That's good. We all used emails. And also like libraries like Kafka uses Zookeeper, which also uses distributed. Ooh, that's nice. Okay, 9%, good. Okay, let me know if you're done. You can look up and we can move on to the next question. I think most people are good. Okay, cool, let's move on. Next question. Can you describe the details of one of the consensus algorithms used in distributed systems? And by describe, I mean, can you describe what it is? And can you describe the details of how to implement it or how it works? And again, look up if you're finished so that I know we can move on. Ooh, someone said, absolutely, this is easy. I love it. Talk to me afterwards. I'm not going to test anyone. Okay, looks like most of us are done. Okay, cool. So as you can see the results, almost everyone, come on, computer. Okay, almost everyone said we've used 96%, that we've used distributed system related software and libraries, but only a few says that they actually understand how consensus algorithms works. So the purpose of this talk is to close this gap. So I'm going to help people to understand how consensus algorithm works in distributed systems. So let's switch back to the presentation. There we go. Okay. Okay, so let's first define what is a distributed system. You can think of the components that are located in different parts of the network, and they communicate with each other through sending each other messages. And some of the modern examples, as we mentioned, for example, the web uses distributed systems because you can think of the clients are web browsers and they talk with the servers who are the central server, and also DNS and BitTorrent. None of us have used any torrent things. Nobody knows what that is. And a fun fact, so in 1920s, the American Central Airline had an office in the center, and traveling agents would call in and ask if a seat has been sold yet. If it's not, they will mark the seat as sold, and if it's sold, they will just check what are the other seats that are available. So this is a very early example of distributed systems. Distributed systems are actually really, really great. It helps us to solve a lot of problems in life, but there are also challenges when it comes to implementing the systems. Well, what are those? So first of all, the lack of global knowledge. Since we have a bunch of computers trying to talk with each other, no computer, no machine actually has the global knowledge of everything. So they communicate via message exchange. So how do we really make sure that the messages are up to date? And how do we deal with inconsistencies? Again, time. So we have different computers trying to work together, but then they all have their own time. So how do we deal with clock skews? And when we have duplicate and delayed messages, how do we know which message got to the machine first? And how do we deal with inconsistency problems? Since we're working with distributed systems, it's very common and likely that we're doing multiple operations on one single object. When that happens, how do we make sure that the object is in a consistent state? And how do we deal with conflicts on the object? Leslie Lamport mentioned that a distributed system is a bunch of machines, and where some other machine's failure that you don't even know where that machine is could cause your own machine unusable. So how do we make our machines to be fault tolerant? And by tolerate, we mean how do we detect the failures? How do we handle them? How do we recover from them? So luckily, we have consensus algorithms, and that helps us with a lot of problems that we mentioned. And today I'm going to briefly introduce two consensus algorithms, Raft and Paxos. So let's start with Paxos. Paxos has a really colorful background compared to the other algorithms. It was implemented and created by Lynch and Liskov at the beginning, but they couldn't really find a mathematical proof at the beginning. So Leslie Lamport found this paper with a malicious intention. And he said, I'm going to prove this wrong. So he worked really hard on this, and he accidentally proved it right. So he wrote this paper called The Part-Time Parliament, and he had a really cute story of how the island of Paxos and the game and all the great fancy names, and to try to explain how Paxos works. The paper for review, but he got rejected because nobody could really understand what he's talking about. People got hung up with the names and everything. So after 10 years, he eventually got the paper published. After 10 years, yes. And one day, I was someday in 2001, he was at a conference and people were asking him, what is this Paxos thing? We don't really understand. Could you please explain? And he said, okay. So he sat down with the people, and then he didn't really walk through the story, but instead he just simply explained Paxos, and people understood. So he went home, he wrote a paper called Paxos Made Simple, which explains how Paxos works without the story. And now people understood what Paxos is. And then later, he published another paper called Multi-Paxos. Basically, the paper is not called Multi-Paxos, but he modified the Paxos to make Multi-Paxos. And then it's basically Paxos plus complexity, which we'll talk about later. And just to show you the proof, I'm not making any of these up. He actually wrote the story in his abstract in the paper. So if you have time to read it, it's really fun. Okay, let's talk about basic Paxos. Actually, no, let's forget about Paxos. Let's just talk about cakes. So I have problem choosing between chocolate cake and cheesecake. How many of you have the same problem? Okay, a few. Okay, good. So how do I do this? Let's just say after this talk, we're gonna all go out and we're gonna just buy one flavor we have to choose between chocolate cake and cheesecake. We have to pick one. And as a group, we have to reach consensus. How do we do this as a group? How this usually happens is someone will say, hey, have we decided yet? And another person will say, not really, we don't know what to choose. And then the person will say, well, let's just go for cheesecake. And then the rest of people will be like, oh, sure, yeah, cheesecake, whoo. And then consensus, ta-da. And that's Paxos. That's literally Paxos. So you have this idea of a proposer, which will propose a value, and then you have acceptor in your algorithms, which the machines will accept and reject values. So let's walk through this step by step. As a proposer, you first propose a number. The number has to be the highest number you've ever seen. And then you're going to broadcast your number to everyone, basically asking them, did we agree on picking a flavor yet? So you send out the number to all the machines, you expect a response. And then the acceptors will accept this proposal number, and they will check, is this current proposal number the largest I've ever seen? If it is, that means this current proposer is the leader. So I'm going to just respond a promise saying that I promise you I will not accept another machine's value unless their proposal number is larger. So after that, as a proposer, if I received a majority amount of responses, that means I can go ahead and propose a value. So now I can just go ahead, say, let's choose cheesecake. And now I broadcast this accept message with my proposal number and the value that I'm proposing to all of the machines. And the machines will respond. And again, before they respond, they first have to check, is this proposal number still the largest that I've ever seen? Basically, they're checking, is this proposer the same proposer as the one that I've made my promise to? And then if it is, we're going to accept the proposal. We're going to also update our proposal number. So as a proposer, we're going to, I realized the typo. Sorry, proposer, I spelled it wrong. So if I got a majority of responses from my followers, I'm going to check, did anyone rejected me? If yes, that means my proposal number isn't the largest one anymore. So I'm going to have to redo this from the beginning. But if I did get a majority of responses and I didn't get anybody to reject me, that means my value is chosen. So I can go ahead, and that means we've got to consensus that we all agreed we're going to choose cheesecake. And enjoy cheesecake. Okay, so what is this proposal number thing that we keep mentioning? Basically, it's a combination between server ID and round number. Server ID guarantees the uniqueness of the number, and the round number gets incremented over time. All the machines share this round number with each other, and also they keep track of the highest round number. So to generate a new proposal number, you simply just increment your max round number and then concat it with your server ID. Multi-Paxos is basically, you can think of it as implementations of basic Paxos. It's a sequence of instances of basic Paxos working together around log entries. And this is how it works. You have a client who's going to send a command to the leader, asking the leader to do something. And the leader will use basic Paxos, which are the steps that we just talked about, to choose command values for each log entry. Once they agreed on which command to choose for a current log entry, they're going to make sure that they apply all the previous command are applied in the log before applying the current command. And then the leader will return the result to the client. So as a leader in Paxos, the leader is distinguished proposer, which means that the leader is the only machine that's eligible to propose values. This is basically designed this way to improve the efficiency, because we don't want machines constantly have to switch leaders and try to propose new proposal numbers. The leader is responsible for sending heartbeat to other machines, basically saying, I am still alive and please treat me as a leader. The leader is also responsible for accepting requests from the client and also process the request and return it to the client. So the followers, if they didn't receive a heartbeat within a certain amount of time, that means they will assume that the leader has died or there was a network partition or whatever happened. They're going to go through the process of electing a new leader, basically trying to propose values. So if everything works well, the non-leader, the followers, will redirect client requests to the leader and act as an acceptor to accept leaders' values. So in Paxos, it's unlikely to have two leaders at the same time because of the way that the algorithm is designed. But Paxos can handle multiple leaders. It will just not be as efficient as having one leader. There are some industry examples that uses Paxos-like algorithms. So for example, Google Chubby and Apache Zookeeper. Did I say it right? Google Chubby? Okay, good. Okay, let's talk about Raft. Raft was designed by Diego Ongaro and John Osterhott at Stanford. People recognize in the industry that Raft is a simpler version of Paxos. But I think when people say simpler version, they don't necessarily mean that Raft logic-wise is simpler to implement, but rather because the Raft paper explained a lot more details in the original paper about how to implement Raft, that makes our job easier, right? Basically, it's easier to understand how Raft works and how to implement it than Paxos. So that's why people say that Raft is simpler. But in terms of performance and fault tolerance, Raft is equivalent to Paxos. On top of consistency and correctness, Raft was designed also based on understandability. So the professors designed the algorithm based on how well they focused on making the algorithm easy to understand, basically. And why did they do this? So basically, if you think about this, in the industry, we usually choose an algorithm that will work well for our system. But when we actually use it in our system, we're going to have to twist this a little sometimes to make it work well with our system. And now we really have to understand the algorithm before doing this. Therefore, you really want people to understand your algorithm before letting them twist your algorithm, because things could go wrong. So making your algorithm understandable is really important if you want people to actually use it. And let's talk about Cake again. So different from Paxos, Raft work around logs. So basically, okay. So what I'm gonna pick someone. Can I get your name? Alex, nice meeting you. Can I use your name? Okay, cool. Pick a cake flavor. Oh yes. Okay. I was just thinking about the same. So Alex picked chocolate. We're gonna trust you because you're best ever at picking chocolate cake flavors or whatever, picking cake flavors in general. So as a group, we trust you as a leader. Whatever you say, we're just gonna follow you. And here we go. We just demonstrated how Raft works. It's not a joke. I'm serious. This is how Raft works. So in Raft, we have two phases: leader election, where you select one machine to be the leader. And then when the leader crashes, you're gonna re-elect. And then the second phase, as followers, we just follow the leader. Whatever the leader say, we replicate the leader's log. And a brief intro to leader election. Basically, all the machines, they have a random timeout number. After they've timed out, The number usually ranges from 100 milliseconds to 300 milliseconds, depending on how you implement any algorithm. The number could differ, but in general, that's the number. So the machines all get a timeout time, and then someone will time out first and become a candidate. And once a machine times out, it will increment its current term. The term number just keeps track of the election term. And also the machine that timed out will vote for itself, and then it will send a request vote remote procedure call to all the other machines trying to ask for a vote. So basically three things, three different possibility could happen from here. One, the most optimal case, we get a majority amount of vote from the other servers. In this case, the candidate will become a leader, and it will start acting like a leader. So basically start sending heartbeats to the other machines and also handle client requests. But what if during the trying to gathering vote cases, the candidate received a heartbeat from the leader? In that case, the candidate will know that there is already another machine that timed out before this current machine. So it's going to step down to become a follower. And then start redirecting client requests to the current leader. And then there's a third case, which doesn't really happen often, but it's likely. There is a possibility of it happening. Basically, it's a split vote scenario, which means that two candidates are competing for votes, and they have a dilemma where none of them have the majority amount of votes from the other servers. In this case, they will both time out and re-enter the election state, so we start all over again.
Quick question.
Yes.
All of this so far assumes you know the value of n.
Yes, you have to, n just means the number of machines. So yes, to get a majority amount of vote, you obviously have to know how many machines are there in the network. Good question. So how do we really? Yes, it is, but it's not something that the consensus algorithm is designed to deal with. Not the current one that I'm talking about. So how do we ensure leader election works? So basically, we guarantee that there is only one leader elected per term. How do we ensure that? Basically, one server only vote once, including for itself. So you have to have the majority amount of vote to win the election. The majority amount of vote is n divided by 2 plus 1. So one example here would be, you can see server 0 is voting for itself, and then server 2 and 3 are both voting for 0. And then server 1 is voting for itself, and then server 4 is voting for 1. And now, obviously, server 0 wins the majority amount of votes, and it will become a leader. So because of this, there will eventually be one leader will be elected. Yes.
In the example you had where 3 servers voted for server 0 and some servers voted server 1. So server 0 wins that election. How does server 1 and server 4 find out that they should actually be following server 0?
Yeah, so great question. As we mentioned before, if a server, during their candidacy phase, if they received a heartbeat from the actual leader, they will become a follower, right? So once server 0 knows that it's elected as a leader, it will start sending heartbeats to other machines. And now 1 and 4 both know that, okay, there is already a leader. I need to follow the leader.
So in the previous slide, you said if I'm a candidate and I get a heartbeat, then that means I should stop campaigning and follow.
Mm-hmm.
Is that also true? So that applies to server 1 in the example you had. Is that also true for server 4? Is just, if I get a heartbeat, period, I just start following who that is?
Yep, exactly. You only vote for other people if someone requested it. And if someone requested, that means you're at the election phase. But if there is any heartbeats, that means you're done with the election. You need to do the log replication phase, where you're no longer submitting votes to anyone. You're just gonna follow the leader. There is already a leader. That's what it means. Cool, yeah.
Maybe I missed it. Why do server 2 and 3 choose server 0 as the
Because I made it so. Well, it's gonna take a lot more time to like actually create the scenario and explain everything from top to bottom. So we don't have that kind of time. So you can just assume that it's great.
What is the hand wave? Do they have like some?
I will have slides who like later talk about how like who gets elected and who can collect votes. Great question though. Yes. Yeah, go ahead.
So it seems like peers who are more likely to be decent. So why is that a good quality?
So basically in our distributed system, in Raft, our goal is in leader election phase is to elect a leader, right? And what you want to do is that you don't want to vote for someone who has an incomplete log, which we'll talk about later. I will give more examples about that. But as long as the candidate has a complete log, then you can vote for the candidate. So you don't know who's going to be the best, but what your goal is to choose someone who's not bad. That's our goal, to elect a leader. We'll talk about the election thing more. I know we have a lot of questions right now, but if you see the later slides, a lot of questions will be answered. So there will did we talk about this? I don't remember anymore. It's guaranteed in Raft that there eventually will be a leader, and then we have a random election timeout from 100 to 300 based on, again, how your algorithm is implemented in your environment. Usually how it happens is one machine will get timed out first, and the machine will become a candidate, and hopefully the machine, usually, it will collect the most majority amount of votes and then become a leader. However, there are cases where two machines timed out at the same time and they are collecting votes and they have this split vote scenario where neither of them got a majority amount of vote. So now they will time out and then re-enter the election state and start over again. Next one. Okay, in the log replication phase, this is how it works. Now, basically, we passed the time when we heard Alex said, we elected Alex as a leader. And now she said, we're going to all go for talk like cake. So this is the phase where we listen to her and replicate the log. So how it works is the client will send a command to the machine, and the leader will append the command to its own entry. I feel like this microphone sometimes works, sometimes doesn't.
It does seem to be cutting out. Yeah.
Okay, so it's not my ear. Okay, good. I don't have to see a doctor. Good. Where am I? Okay, and then once the leader append an entry to his own log, it will send an append entry remote procedure call to the other machines and asking them, hello, I've appended this command to my own log, and please do the same. The other machines will listen to the leader and append the command to its own log, and then reply an acknowledgement telling the leader, I have already appended this entry and acknowledge you that I've done so. And now if the leader receive a majority amount of responses, that means it's safe to commit this entry. Basically, it's safe to execute the command and also return the result to the follower. So after that, the leader will also notify all the followers that I've committed this entry, and please do the same in your log as well. So we've covered if everything works well, right? If all the followers responded the leader, the acknowledgement, if we get a majority, we're going to process the request and whatever. But what if we don't receive the majority as a leader? So in this case, the example here, we send out all the requests to our client, but not the majority responded. We didn't get the majority response. So in this case, in Raft protocol, the leader will just keep trying until everyone has, well, not everyone, but the majority has responded before moving on. We kept talking about the log entry. This is what it looked like. Basically, you have a term which keeps track of the current term that the most recent leader was elected, basically the current leader. And then also the command to execute for this current entry. And you also know the index of the current entry. We'll need this information later. So how do we ensure the log consistency? One example here would be, example of inconsistent log would be, you can see server 0 and server 2 has a longer log compared to server 1. So that could happen based on, either there was a network partition that server 1 was outside, wasn't communicating or receiving anything from the other servers, or it could be that server 1 just crashed. How do we make sure log is consistent? This is, again, circling back to the question that was about how do we elect people, it's going to be covered here. So basically, we make sure log is consistent using two things. One, we always trust the leader's log. We do not elect candidates that we don't believe that has a complete log. And we're going to give more examples later. We always append entries to the log. We do not allow any holes in the log, so we don't skip entries. We always append to the end. We also repair inconsistencies in the log during log replication times. So let's talk about the first one. How do we ensure that the leader's log is complete? Basically, in the request vote remote procedure call, there are 4 things that are required. Term, which means what is the current candidate's term. Remember the term number that we kept talking about? Basically, that is when was the last leader was elected, and then once you become a candidate, you increment your term. So this term is the candidate's term. And then the ID, also the last log index. So what was the index of your last log entry? And also what was the term inside of your last log entry? So one example would be, let's say we have candidate as the blue one, and then the current state machine, our machine, is the green one. So here are all the information that we have about us and also the other candidate. We can walk through this example together. So we have the candidate term as 2, our term is 3, the candidate ID and our own ID, which are different, which that's expected. Our candidate last log index is 3. And our index is also 3. Last log term of the candidate is 1, and our last log term is also 1. Should we vote for the candidate or not? So the answer is that we do not vote. We reject the vote because the candidate's term is less than our term. That means we've been through more elections. That means we know more than the candidates. That means we probably have a more complete knowledge of what has happened. So that answers someone's question. I don't remember who asked that, but that answers someone's question about how do you elect the right leader? Okay, I think it was you, right? So how do you elect the right, what's your name, sorry? Yeah, Yuan? Thanks for asking, but this is how you guarantee a leader, the elected leader has a complete log. Basically, you compare to see what information the leader has or the candidate has and to compare it with your own information, try to make sure that you don't elect the wrong machine. And let's go through more examples. We all love quiz. So let's turn those into quizzes just to make sure nobody's sleeping. So let's walk through this example together. We have, again, the candidate in the blue, and then current machine is green. And then in the request vote RPC, the candidate's term is 3, and then we have the same term. So that's good, check mark. And then the IDs are different, that's expected. The candidate's last log index is 3, and our last log index is 4. And then we have the last log term. Raise your hand if you think we should vote for the candidate. Whoa. Raise your hand if you think we shouldn't vote for the candidate. Oh, yes, everyone got it. Okay, great. Thank you. So someone has a question?
In this case, would the request vote be a term of 4? Because they would be doing the next election cycle?
That depends. It could be that our own current state machine is also a candidate and they're both collecting vote. You don't know that, right? So it's possible that they have the same term. It's definitely possible. And then, we reject this candidate because our log index is is larger, that means we have a more complete log. So we deny the candidate. Our log is longer, we do not vote. Yes.
So when you lose a leader,
Yeah.
does everybody say, I'll do it? Does everybody submit their logs and okay, I'll do it?
Great question. So that circles back to the leader election phase. They would expect heartbeats from the leader, remember? And then leader, once they stop receiving heartbeats, all the machines will know, oh, the leader died. So we're gonna have to re-elect someone as a leader. But then they will get a random timeout time. All the machines will have a random timeout time. Whoever times out first will start collecting votes first. But doesn't mean that the candidate who time out first is going to win the election. Obviously, this phase checks if their log is complete or not, right? So if their log is complete or as complete as the other machines, then the candidate will become a leader. So let's go. Yes.
So is the purpose of the random timeout then to make it so that among the candidates who have the same state, to sort of like randomly pick one of them arbitrarily?
Sorry, say that again.
So there's a couple things determining who becomes the leader, right?
Yes.
One is who's got the most complete state committed,
Right.
and then the other one is this sort of randomized parameter, right? So the
Right.
question is the reason for the randomization there just to make an arbitrary choice among the people who have the same state?
Well, the random election timeout is basically make sure that the whole distributed system do not stuck there, right? Someone has to stand up. Is that the right word? Stand up and become a candidate and start to collect vote first.
Okay.
So that's what that is for. And okay, let's go. Oh, we have more questions.
Are you going to cover in a future slide what's the information that goes on a heartbeat?
Heartbeat. Oh, so what's a heartbeat? You're asking?
What's information that is sent on a heartbeat?
Yeah, that actually.
Here you're showing that from the request vote RPC, we are sending 4 pieces of information at least. The heartbeat, I assume that it also contains some information.
Yes, actually, I've seen different implementations of that, but I believe in the paper, I will also cover that later, but in the paper, the heartbeat has a pen entry RPC, which has a list of information that I will cover later. Yeah.
How do you guarantee that, you said earlier that you always end up electing someone, but how do you guarantee that you don't end up always rejecting somebody? So for example, one machine has a shorter log and the other one has a higher term or something, and they keep rejecting each other. Is that possible?
Well, eventually you will have, so if that happens, that means maybe, let's just say we have 5 machines and one machine has the most complete log. The rest didn't have any complete logs. Basically, in that case, the leader, well, the machine with the longest log will obviously be elected later, but it will just take more time to get to it because it has to go to a phases where it needs to reject other candidates, and eventually this longest log machine will time out and then it will be elected. So it will take amount of time to get to there, but yes, there eventually will be a leader elected.
If a candidate does an RPC to a machine and that machine has a longer log, does that candidate drop out? Is that what happens?
Well, so you're saying during leader election phase?
Well, no, during this phase, like when the leader dies.
Yeah.
And then you're doing these requests to see who has the longest log.
Right.
Like, if another machine has a longer log, wouldn't you drop out? Like, is that how you're able to assume that the longest log one?
You don't drop out, but instead you just won't collect the majority amount of votes, and as a result, you won't become a leader. That's how it works. Yeah.
Seems like it'd be really easy for, say, a third of the machines to get by more than one message, because the leader, got 50% plus 1 for a message, got 50% plus 1 for a message, and then does it keep retrying?
If it gets a majority amount of votes, that means it can become a leader now.
Yeah, it can proceed.
Yeah.
But in proceeding,
Right.
could it not leave behind a bunch of nodes so that, now you're carrying 51% of the original N? And
Yes.
that's sustaining you.
Right.
But now 49% of your nodes are effectively dead, or do they have a way of catching up?
I think you mentioned there was a way to repair log replication.
Right. That will be mentioned in the later slides. Yes.
Maybe you're gonna cover it. But
Yeah. So sorry. I will let you finish. Go ahead.
It seems like if you have really bad communication and only one guy got the right log, you could converge on somebody other than him if everybody keeps timing out earlier and voting for each other.
The problem is no one has the global knowledge, right? So all the machines they only have their own. They have the knowledge of themselves, and also whoever is requesting vote, they send this little tag that contains those 4 information. That's all they know. So no machines has any global knowledge of everything. That's at the beginning we've mentioned that. That's one of the challenges that we're dealing with in distributed system. I just want to mention one thing. A lot of things will be covered in the later slides. So if you want to ask, that means that I did a good job at doing the slides, right? But yeah, thank you. But I also want to say that I don't want to take more than an hour spend due to this talk. We probably have a limit on the room and whatever. So maybe wait a little when you ask questions. I definitely take questions at the end, and I can also give my emails and send me emails and whatever, but maybe we should wait a little before asking questions. Go ahead.
I was going to say, I think in the scenario you're talking about, if I understood what you said earlier,
Yeah.
those rights wouldn't have been committed because they already rights back from the logs. If you got one log ahead, that would be rights that were committed.
Let's keep going.
Okay, good. Let's keep going. So where are we? Okay, so next example. What do you think about this? Another quiz. Do you want me to walk you through this? No, okay. Raise your hand if you think we should vote for the candidate. Oh, good. Raise your hand if you think we shouldn't. I mean, I basically sold myself by saying good, but yes, we accept the request. We vote for this candidate because we have the same term and the candidate's log is longer. So we think that the candidate has a more complete log. So we vote for this candidate. Okay, let's talk about repair inconsistencies during log replication, which seems like there are a lot of questions about this. So append entry RPC contains the following information. Basically, it has everything about the current last entry. So in that example on the left, so we contain all the information about the last log entry, the index, the term, and the command, and also the index and the term of the previous entry before the last entry. And depending on the implementation, most people, I think, send this RPC as a heartbeat as well. So that answers someone's question about the heartbeat. So the purpose of sending all those information is once, as a leader, if we require our candidate to append a log entry to its own log, it's going to send those 5 things to the candidate. And the receiver received this information and is going to do this. It's going to check to see if the preceding entry, so basically I'm gonna move. So basically it's gonna check, is this current entry has the same kind of information as my entry. So it will check at index 4, does my own log have a term of 2? If yes, that means it's safe for us to follow the leader. That means everything before this index, before entry 4, everything before that, it's all identical to the leader's log. So we're just gonna copy entry 5 to our own log. And if it doesn't match, then we're gonna reject it because that means it could be that this current entry does not match the leader's entry, or it could be anything before that didn't match. We don't know that. So it's safe for us to reject the leader. So what's going to happen is that the leader will just move the pointer to the previous one. So basically it's gonna send entry 4 and 5 and the index and term of entry 3. So it's gonna send all those information to our candidate and candidate follower. And then the follower will check at index 3, do we have the same term with the leader? So now they match. So we know that everything before entry 3, including entry 3, everything is the same as the leaders. So we just copy 4 and 5 to our own log. That's how you replicate log and fix inconsistencies in your own log. So because of that, we can rely on this log matching property that is used in Raft. For each log entry, you basically compare the index and the term of the log. If at a certain index, if the term are identical, that means 2 entries have the same command. And everything before this entry are all identical. So one example would be if you look at server 0 and 1, at index 5, they have both term 2. And because of that, we can assume 2 things. 1, they have the same command in the log entry. 2, every single entry before this current entry are all identical. So those are the 2 things that we can use. It's called the log matching property. And as a counterexample, 0 and 2, they do not have matching term at 1 index. So therefore, you can't really assume everything before this is going to be identical. Is there any problem? I actually drew this. I think I did a great job. So is there any problem with consensus algorithms? Obviously, yes. What are the problems? Well, we said that the machines communicate with each other by sending messages, and therefore we're going to have a huge amount of overhead because for every single step, we're going to have to send messages among each other and trying to do something, trying to agree on one value. So how do we, when you use your consensus algorithms or when you implement one, you need to think about how do you handle duplicate messages? How do you handle out of order messages? What about the messages that get lost? How do you know about those messages? How do you get them back? And how do you deal with network latencies? Those are the problems that we all have to handle when we implement the consensus algorithms. Also, there are machine failures. We can have leader failures and also follower failures. We could have network partitions, which won't allow the machines to effectively communicate with each other. How do we handle those problems? How do we know that there are problems? How do we keep the confidentiality? Which machine has the right to read? Which machine has the right to write? And I actually apologize for this picture. I don't know how to draw it in a less creepier way. So this is like the best I could do. So whatever. If you have any suggestions, talk to me later. Okay, this is much better. A dinosaur. So how do I handle malicious peers and misbehaving peers? Other machines could come and abuse the information. How do we prevent them from doing that? And one example of misbehaved peers is Byzantine generals problem. Basically, the story is you have 2 generals, and they're trying to decide whether they want to both attack a castle or retreat from it. And it's very simple. They basically have to agree on one decision, but they can only communicate through a messenger. So the problem seems really simple, right? So if they both agree to retreat or to attack, they win. But if they make the decision that is different from the other general, they will lose. So it seems really simple to solve this problem. The hard part is you can't really trust the other general. You don't know if the other general is a traitor or not. And that applies in distributed system as Byzantine failures, which basically you have a node that's behaving exactly the way it's expected. And then it's sending messages and receiving messages. It's not showing any signs of being compromised, but it's a malicious node. So it could send malicious stuff, RPCs, to your other machines, and it could eventually destroy the whole system. Are there any Byzantine fault-tolerant algorithms? Yes, there are. There are modified Paxos and Raft that deal with Byzantine fault-tolerant Byzantine failures, but when you're implementing those algorithms, you need to step back a little because those algorithms proven in many people's research that it's really, really costly in terms of complexity and everything. It costs a lot more to implement those algorithms. Some of the takeaways. Finally get to the end. When you're implementing the consensus algorithm in the industry, well, when you're trying to do that, the first suggestion is don't do that. If you can find someone's work that's implement a well-written consensus algorithm and that has been proven that it works well, maybe it's a good idea to use the work, because implementing a consensus algorithm is a whole different story from explaining it or trying to understand it. When you're implementing it, you need to think about the problems that we mentioned. Is your system resilient against all those issues and more? And also, when you do have to implement it, you also need to think, do I want my algorithm to be resilient against those problems? For example, not all the machines needs to be Byzantine fault tolerant. And it's a trade-off between reliability and complexity. You need to make the decision when you're implementing the algorithms. Also, in the academia, when we're designing consensus algorithms, not only we need to consider consistency, correctness, and all the things that we need to consider, but also understandability. We want to design an algorithm that can be understood by people in the industry and everyone else. I don't know why I just said that, but we want to design an algorithm that can be understood by everyone. I'm not excluding anyone. And therefore, people can actually use the algorithm to apply it to their own work to make the algorithm actually useful. And that concludes my talk. So thank you. Well, before we do the clapping thing, wait, I want to ask. I'm just out of curiosity. How many of you love cheesecake? Can you please raise your hand? Oh, okay. What about chocolate cake? Oh, it's hard. It's got 50-50. It's so hard to choose. Okay, now we can clap. Thank you. I'll take questions. Yes.
So I had asked about the format of information carrying heartbeat, because what prevents one of the computers from just randomly spamming everybody with heartbeats saying, hey, I'm the leader, preventing anybody from actually becoming the leader?
Well, the purpose is that you don't always go back to leader election. If you're a leader and if everyone else knows that you're a leader, then your role is to maintain your leader status. You're going to process your client request and you're going to do the log replication. So the goal of Raft is not to constantly pick leaders. That's the purpose of heartbeats, is to prevent people to become leaders, because there is a leader in the system. So that's exactly what it's doing.
What are typical use cases for these?
Oh, good question. I think I mentioned that for Paxos, Google Chubby uses Paxos-like algorithms, and also Zookeeper implement. So how do I explain this? You want to can you explain?
Distributed state. So we'll use something like this, not for like the meaty part of what they're trying to do, but just for like some of these leader election features. So like if you've got 5 replicas, they'll use something like this to choose which one of them should be sort of like the canonical one that everyone should pay attention to. Right? So you might have some kind of like database system where one of the nodes is responsible for sort of maintaining the master copy of like what the current state of the database is. And they would use something like this to figure out which one of them has that responsibility at any given point in time.
Yeah.
For the log replication or log correction phase, do all your commands need to be reversible? So if I'm like ahead of someone, like I've got term 2 or term 1, I have a longer log, so I don't line up, and I have to like undo that term. How does that work?
That's a good question. So you're saying you know that your log is inconsistent, and you need to copy the leader's log to replace yours.
Yeah.
That means you will have to run whatever the command in the log again on your system to make sure that you are at the same state as the leader.
I think in the worst case, you can replay the leader's log into your own state. As an optimization, you might make it reversible.
Yeah, and also the log, it will never happen if you follow everything in the protocol. I think I understand what you're asking is basically if let's say there is command 1 and command 2. If I already applied command 2, do I have to go back to 1? How do I do that?
Yeah.
But the thing is, if you follow all the things in the protocol correctly, you will never be one step ahead of the leader. Because if your log is inconsistent, if the leader, we can always trust the leader's log because the leader won't be elected if the leader's log is incomplete, right? So if there's any difference between my log and the leader's log, we always go to the leader's log. And now, since we can't be a step ahead of the leader's log, that means whatever command we have in this current log entry is an old command. So we don't have to reverse it because all the machines have applied this command, and so did I. So I just simply have to replace my current entry and apply the new command. Does that make sense? The back first.
Isabel, let's go in a network segmentation case. Let's say half your nodes network segment, others other networks.
Yeah.
But within that realm, they feel like they're fully up, operational, accepting requests, performing commands.
Yep.
I'm curious about, the sort of the pattern of when they either rejoin or the issues around the period of time that they are segmented and kind of like how do they recover?
Yeah, that question has a very, very long answer.
It's like theoretically in both those models, like there will be a leader that's elected unless they have knowledge that there aren't the right number of nodes somehow, and like.
Actually, there's a very simple answer. It's called cap theorem.
That's very short.
Very short answer. It's called cap theorem.
Could you explain that?
You can get consistency, availability, partition resilience. Choose any two. You can't have all three.
I think he's looking for a more.
So if you want partition resilience, you want availability or you want consistency?
That's really vague.
Right.
If you want consistency and availability, you have to give up partition resilience.
With both of these algorithms, the number of nodes that need to agree is given outside the algorithm.
Sorry, say that again.
In both of these algorithms, the size of the cluster that's coming to consensus is given outside of the algorithm. So you can't have a partition that has two majorities. You can't wind up with two competing.
Yeah, you can't. So the end is constant. You can't have two partitions that has both has majorities, right? Does that make sense?
It's given and odd.
Doesn't have to.
Because if it's even, then it might split exactly in the worst way, and then you would have. Well, I guess that's not a choice. That's
But
not
the
a
thing
choice.
is,
Then
okay.
neither will make progress.
But the thing is, when the partition goes away, there will be someone with the most complete log, and they the leaders. If let's say we have two leaders, right, and they both think that they're the leader, they will send heartbeats to all the machines. But whoever has the more complete log is going to eventually be the leader, and the leader that it has a shorter log will step down as a follower. So we won't end up having two leader all the time. Once the partition goes away, we'll eventually have one leader. I think that could briefly answer your question, but what you asked.
You should never end up with two leaders.
Yeah.
After the, if you're only ever elected a leader with the majority of the votes,
Yeah.
you would never have two leaders.
Yeah, one side of the partition would just get stuck and.
Oh, I mean, when the partition goes away.
The way I've seen Raft implemented in reality is you have a certain, based on the number of nodes you have and the amount it takes to reach a quorum or a majority, you're able to handle X amount of node failures before you lose consistency and have to stop taking. So you literally if you're going to have actually implement that, you just have to realize that I can lose X amount of nodes based on how many I have. I don't know the exact ratio, but you just have to design your system to handle the amount of node failures you're prepared for.
But her point is you need an algorithm to determine N that's not part of the consensus out.
No, that was. David asked that at the beginning, right? So this is based, N is given, right?
N is given.
But if N changes,
N
you have
doesn't
to have,
change.
that occurs outside the algorithm.
If a node fails, that doesn't change N. N is saying, I expect there to be 5 nodes, and if one failed, there might be only 4 that are working right now, but N is still 5.
Yes,
And of those 4 nodes, 3 still have to agree to give you a majority.
exactly.
What if you're down to 2?
Then you just can't work.
Then the
You're
Paxos
down.
theorem says you've sacrificed availability and you're not going to be able to respond to any requests.
Exactly.
Yes, correct.
So I have, I guess, as much an observation as a question. I read the paper and a while ago, but everything basically was at the edge of making sense, except the part where
Which one? Which paper you're talking
the
about?
original one, the Raft.
Raft. Okay.
Raft, yeah. When the node goes away, not just for a little while, but just disappears, then you need to add a fresh new node to the system. That's the part which was like, I don't think the original paper fully addressed it really. I think if you know for sure, I guess if you have some kind of like, a little, orchestrating system or something that knows for sure that the node is no longer there, I guess it could just say, oh, here's a new node which is like the same identity, the same ID as the old one, okay, and it's just like if the old one came back. But if you are concerned that there may be a network partition or such, no one can know that it actually went away. And my recollection is that there was some kind of extension or some work to basically to do essentially a Raft algorithm for replacing nodes as kind of integrated into the main voting process somehow. I don't know. And that part was like crazy complex in the sense that like I seem to recall Zookeeper had a bug where people couldn't even agree. There's like a center thread. They couldn't even agree if it's a bug or working as intended. So I don't know if you kind of understand how that part works when the node catches fire and disappears and you have to put in a new one.
If I understand you correctly, so let's just go back to the Raft. So first of all, I think Zookeeper actually uses Paxos like algorithm. It doesn't do anything with Raft.
Maybe misremembered, sorry.
So that's one, but also with Raft, we're talking about Raft. If a follower goes away, the other followers won't know because they don't necessarily send each other messages and trying to make sure each other are alive. But the leader will, whether they're gathering, so the leader send out those append entry remote procedure calls, right? So the leader asks them to append entries, and the leader will get acknowledgement, collect acknowledgement. If one node disappears, the leader probably will still have the majority amount of votes. So that doesn't affect the whole system, if that's what you're asking.
Yeah, but then the node disappears now. You want to go back from your 4 nodes to your normal 5. I guess you basically, unless you know for sure that that one disappeared node will never ever come back.
So the purpose of Raft is not to make sure everyone is alive. The purpose of Raft or any of those consensus algorithms is try to make sure that the majority amount of machines is working. As long as we have the majority amount of machines working, we can take care of clients' requests and make sure everything works correctly. We don't try to make sure every single machine is alive. That's definitely a trade-off between availability and, but there might be modified versions where they like replace a node once they notice another node is no longer doing whatever it needs to do, but that doesn't belong to part of Raft.
Most systems seem to defer that to the wisdom of the system.
Yes.
Like, you have to have a way to entirely prepare a node. How many systems that implement this? Maybe like repair from the beginning.
It's like the challenge is you need to know for sure that it just completely disappears, never comes back. That's the tricky part.
Do you have a timeout on?
Yeah.
Return.
Yeah.
Just say, okay, after an hour, you're dead.
Mm-hmm. Yeah, and also that's a good point because again, we mentioned at the beginning that people usually twist the algorithms a little to use it in their own systems, and many different ways of how people handle those kind of failures and all the kind of different things. It really depends on how like the implementation details, basically. Yes.
So there's one thing that wasn't clear to me as a networking kind of person, which is, it appears that at least leader election has a live log. The RTT dispersion of the network is longer than the timeout, which says that if you have a network with fairly big RTT dispersions, you have to set these timeouts really long, right? So if you have RTT dispersions of 2 seconds, which is common on the internet, you may have to set timeouts to be 10 seconds, 15 seconds, 20 seconds. Otherwise, you'll get a live lock at leader election.
Sorry, you meant the timeout for what? For the leader
Timeout for
election?
deciding that somebody's dead.
Oh, the leader election, the leader timeout
Yeah.
time for heartbeat stuff.
Right.
Yeah,
Because
he's saying if
you
that
have to
time
wait for
is shorter than
for
it takes
messages
to
that are
actually
gonna
cross.
To
arrive,
get
or
to,
longer than the timeout, you're gonna get a live lock. Nobody will ever make any progress.
Yeah, that makes
Choose
Which
sense.
is, I think, why these things are only used like when clusters of machines either in the same room or at least in the same data center. They're not like used over, wide area distances across, hundreds of milliseconds of RTT.
Or you have to set the long enough timeout
Yeah.
to deal with
Oh, well,
that.
yeah, I mean,
and
yeah,
long enough
but then what is it useful for?
Well, so, as mentioned earlier, sometimes it's used to elect a leader in another system that's like a master replica setup and direct all the other client access to that, so that the high throughput stuff isn't going through the consensus algorithm.
Yeah, well, you probably don't want to do that over a low latency network either.
No. Yeah, there's all kinds of.
Well, maybe next time you can talk about a useful algorithm here.
SCP tries to solve this problem.
Okay.
Right?
That's a great paper,
called
Colin,
Consensus
here.
Protocol. It tries to solve that problem,
Yeah.
but it's
Okay.
really new work. So.
Okay. Definitely get our email afterwards.
Cool, okay. I think that's it for questions. Thanks, everyone. Let's thank our speaker.
Thank you.